Hi guys, this video is a unique factorization domain. Now there is an example of integral domain in which there is unique factorization into primes. Take an integer 30, factor 30 into primes, 30 equals to 2 into 3 into 5. This factorization of 30 into primes is unique because there is no other way you could factor 30 into primes in integer. So it is an example of unique factorization domain. Now, in order to discuss analogous ideas in an arbitrary integral domain, we define few terms. Now, the first term we have is factor. If A divides B, A is a factor of B. Second term we have is unit. If U divides 1, 1 is a multiplicative identity, U is a unit. In Z, only 1 and minus 1 divides 1, so the units in Z are 1 and minus 1. Third term is associates. If B equals to AU, where U is a unit, then B and A are associates. For example, 2 and minus 2 are associates in Z. Likewise, 5 and minus 5 are associates in Z. The fourth term we have is irreducible. If P not equals to 0 and not equals to 1, and P equals to A times U, where U is a unit, then P is irreducible. For example, 3 equals to 3 into 1. So 3 is irreducible in Z. In fact, all primes in Z are irreducible. Now we are ready to define unique factorization domain. An integral domain D is a unique factorization domain if it satisfies these two conditions. First condition, every element of D that is neither 0 nor 1 can be factored into finite number of irreducibles. Second condition, if P1 PR and Q1 QS are two factorizations of the same element of D into irreducibles, then R equals to S and Qj can be renumbered so that Pi and Qi are associates. That means the total number of factors in these two factorizations are same, R equals to S, and the factors can be reordered such that the corresponding factors are associates. Now let us see what this means with an example in Z. 24 is an integer. The first factorization of 24 into primes is 2 into 2 into 2 into 3. The second factorization of 24 into primes is minus 2 into 2 into minus 3 into 2. The factors in second factorization can be reordered as minus 2 into 2 into 2 into minus 3, such that the corresponding term between these two factorizations are associates. 2 and minus 2 are associates, 2 and 2 are also associates, and likewise 3 and minus 3 are associates. Now the next topic we have is principal ideal domain, PID. An integral domain is a PID if every ideal in it is principal. Now the ideals in Z are 2Z, 3Z and nz. Now these ideals are principal because these ideals they are generated by some element in Z. For example, 2Z it is generated by 2, and likewise nz it is generated by n in Z. So the integral domain Z is a PID, principal ideal domain. And finally we have two important theorems in UFD. First theorem is every PID is a UFD. Every principal ideal domain is a unique factorization domain. For example, the integral domain Z. Z is a PID as well as UFD. We know that. Second is, if an integral domain D is a UFD, then so is its ring of polynomial dx. For example, Z and Zx. We know that the integral domain Z is a UFD and so is the integral domain Zx. And this much for today.